recorded. And yeah, so hi everyone, and welcome to this webinar where I will take you through the steel design capabilities of advanced design. And actually, so before we start, a few words about myself. So I'm Thibaut Frété, and I've been working for Greatech for quite a few years now in France as a senior product specialist now, which means that I'm working on product specification, to make sure that the software is up to date in the normative context, with standards that keep changing with amendments being published. We have to keep up the pace. And I'm also working on product validation. All right, so let's start and talk about steel design. And actually, when you think steel design, it's always more than that, because steel buildings, they can be highly affected by climatic loads, like wind and snow cases. So for an efficient steel design, you will need a strong climatic generator. It starts with that. So you will need a climatic generator that comes with various standards, so you can work on projects all over the world. But you will also need it to be, you need to rely on it in 2D, but also in 3D, because most of your buildings, they will be 3D. So you need it to handle the snow cases, and not just the usual uniform and drifted snow cases, but also all the possible accumulations from the standards, like the accumulation due to a higher building, or the accumulation from parapet walls, or even what we have in some countries, what we call the gutter accumulation. You see, it's when it's raining and the rain is getting trapped into a snow accumulation. Well, you have to consider an extra load strip, and it's very easy to miss on one of these accumulations. If you are aware of them, there are so many that you can really mess things up. So you need a good generator for that. But snow cases are only one thing, because then you've got the wind cases, and they are way more complex, especially in the latest standards. So you will need a generator to handle the usual buildings, like the monopitch ones, the duo pitch ones, and even the vaulted roofs. But you need also one that will handle the unusual buildings, like what if you have a building like an L-shaped building, or a building with vertical discrepancies, because these shapes are not covered in the standards, but doesn't mean they don't exist. Like even building with awnings, they are not properly covered in the Eurocode 1. You have protruding roof, but that's very conservative. So, and yet I'm pretty sure at one point you had to design a building with awnings, like put wind forces on it. So if you stick to the standards, you don't have an optimum solution. And that's why some extra rules have been published recently to complement, like the Eurocode 1. We have them for France, for Belgium. We have rules that tell you how to handle these complex cases, like which wind zones you should have, which coefficient, like pressure coefficient values you should have in these zones. And yeah, these rules, they're making their way to other European countries, and they will lead to an update of the Eurocode 1, of the standards. So maybe you're just hearing about them now, but by the time the Eurocode 1 is updated, well, be assured that they will have been implemented in advanced design for quite a long time. So once you get your climatic loads correct, you can actually think about steel design and the complex effects, like buckling and lateral torsional buckling. And for that, you need a software that will let you define these assumptions and do it easily and quickly. You know, for example, for lateral torsional buckling, if you want to reduce these effects, oh, I got a message. Okay, it definitely could wait. So, yeah, if you want to reduce the lateral torsional buckling effects, you will need to put restraints, and you need to do it easily. You don't want to open dialogue after dialogue just to help you a bit on the work ratio. So you need to do it graphically, like in advanced design. You see, in advanced design, you can just select an element and click where you want to put restraints. It's all graphic, no need to open a dialogue. And not only that, but these restraints definition, they can be reused for the buckling in the weak axis, because lateral torsional buckling and buckling in the weak axis, they're pretty much the same. So you can reuse this restraint definition to save even more time. And to help you even more in defining these complex design assumptions, be aware that advanced design comes with a set of predefined design templates for command members, like for rafters, for columns, for purlins. And not only do they have this sensible buckling and lateral torsional buckling assumptions, but they also come with predefined deflection settings. And that way you can focus on even more complex aspects, like you know, the imperfections. The imperfection is probably the most complex part of the steel design standard. Like in the Eurocode 3, it's so complex that you want it to be an automated process. You don't want to input tons of parameters that you can get wrong. You want a software to handle most of the part, because you have the global flow imperfections to worry about, and these ones stand for a lack of verticality in the columns, but you also have the local bow imperfections. They stand for an initial eccentricity, which will cause buckling in the columns. And then, these local bow imperfections are actually very tricky because they depend on the buckling curve. But you don't want the user to impose a buckling curve. You want it to be an automatic process again. And once you've got all these imperfections, well, you need to be able to run a second order analysis on top of that, because having the imperfections and a second order calculation allows you to neglect the buckling and lateral torsional buckling coefficients. You know, like the XY, the XZ, the XLT, you can ignore them all, because with the imperfection and second order, you've done enough. And having a software doing all that in an automatic process, it lets you focus on just reaching the optimum building solution through a series of optimization. And in advanced design, you can optimize your structure based on strength and stability to make sure that a section is not overused, but it's not underused either, and that the deflection is also checked. And you can even drive the optimization through preferences, like maybe you want the most cost-effective solution, or you're limited by dimensions, like there is a given dimension you cannot exceed. So you can drive your optimization in advanced design. So that's for the Eurocode, like the steel design itself. But sometimes you will have to go beyond the limitations of the standards. Like, what if you have an unusual section? And by unusual, I mean a section which is not covered by the standards, like a section which is not doubly symmetric, you know, like a channel. It's unusual for the standards, but it's quite common in building practice. And this section, what makes it so complex is that it's getting an eccentric loading, you know, because of where the load will be applied. And this eccentric loading will cause torsion, and with torsion comes warping. And warping is when you've got flanges rotating in opposite directions. And it's complex because it causes the cross-section to no longer be plane. and it's very complex to assess. Basic formulas won't stand there, and you will actually need a very sophisticated numerical solution, one that will handle a seventh degree of freedom to account for warping, and one that will perform a modal analysis, because the imperfections will be given by the shape of the critical buckling mode that will be scaled and turned into a displacement. And then you will be able to, you need to run a second order analysis on the member to account for the effects of the deformed geometry. And in advanced design, we do have a method for that. It's what we call the advanced stability, and it will run a second order analysis on the member with warping and with imperfection. So let me show you all that on an advanced design model. So I hope you can see now my advanced design model. If you don't, feel free to type in a message. So this is the model I will be using. So I picked this one because it's small enough that the calculation time won't be an issue. It won't take minutes. It would be very fast, while still being complex enough that I can show you all the features that I've just mentioned, starting with the climatic generator. So if you want to input automatically wind and snow forces, all you need is load areas on the building faces and on the roof. And I do have them. So these load areas, they come with a span direction to distribute the forces they will get, like the wind forces and the snow forces. But you can also assign them some opening parameters, like a given face can be completely open, or you can define an opening ratio. Like here, if I have maybe a huge door, I can put a 20% opening rate. And on this other face, maybe I can put a 15% if I have like windows or things like that. So you can define openings on several faces. Just make sure it doesn't exceed 30%, because then you're not dealing with walls, but you're dealing with a canopy roof, and this is very conservative, so you don't want that. And then you will generate automatically the wind forces by defining a wind family, like here, where you will define where you are. So we are here. You've got all possible. Also, I'm set on France and I'm using the Eurocode 1, but of course we've got the Eurocode 1 with various appendices. We've got American codes and Canadian codes as well. Then we've got all possible reduction coefficients, like the CSCD. We've got the correlation coefficient, like anything to be in favor of the user once activated. Like any parameter from the Eurocode 1, you name it, it's right there. We've even got the return period here. And if you want to generate the forces or to have them generated, you will just right click and automate generation, and instantly you've got all your wind cases. And we've got quite a lot, because the Eurocode 1 tells us to have that much, especially when you're dealing with such a building shape. You know, when you have horizontal discrepancies, considering like a pure X wind or pure Y wind is not enough because of the setback here. Actually, for each main direction, you have to consider a 45 degrees in and a 45 degrees out. So it doubles the load cases, because the wind effects will be completely different. See, let's see what it does for the X wind. See, so this is the X wind, like blowing on the side. So first you will need to consider the X wind with a slight deviation like this. You know, when the X wind is blowing inside the setback. So this is the very first load case. And let me show you what's happening first on walls. So here I can differentiate between the forces on walls and the forces on roof. And that is because I named my load areas. You see here, I named them walls and for roof, I gave them the roof name. That way, I can easily isolate the forces on walls. So it's a nice trick, maybe you're not aware of it. So for walls, you see for the X-wind, when the wind is blowing in the setback, this face is perpendicular, so it will get zone D, this one as well. In the back, you've got zone E with a minimum and negative pressure coefficient. And on the sides, well, you've got your A, B, and C zones, and same thing there, like A, B, and C. So just as expected, very, very classic. But on this face is where it gets complex, because even though this face is, parallel, you would expect it to be A, B, or C, but it's not, because remember that we have a small deviation like this. So the wind is blowing on this face, so it's actually zone D as well, with a maximum positive value. So all these three faces are treated the same. But this is only for the deviation 45 degrees in. When you are 45 degrees out, then things are completely different, or at least different enough that it needs to be a different load case. So let me show you again on walls. So the wind is blowing, it's still X wind, but blowing like this. So this face is like zone D, this one as well. In the back, you've got E, and on the side, you've got A, B, and C. A, B, and C. But you see here on this face, we can notice a change of sign. We have a change of pressure. And this is quite unusual at Euro Code 1. You might think it's a mistake, but it's definitely not, because remember that the wind is blowing and we have a small deviation like this. So this whole part of the building is actually protected because of the setback. And because of this protection, it cannot be zone D. It's actually zone C, because it's zone A, B, and C that is going on. And the length of the protection, like the 12 meters we have here, is not random. It's actually the 12 meters from there that we bring back all the way to make it zone C. So you realize how complex it is, because I've only mentioned what's happening on the walls, but you also have to do this like twice direction. You have to do it for roof as well. So if I just show you very quick on the wall, so when the wind is blowing right inside the setback, you've got all your peak forces, like F, G, and same thing here, G and F. But when there will be a protection effect, you see, you won't get some peak forces there, you will get much smaller forces. And if you want to do it manually, yeah, believe me, it will take maybe a whole day, because it's very tedious. First, you've got to find the zone dimension right. Like when you have a 3 meter by 120, you actually have to use formula for each dimension. And then, once the zone are right, you have to find the right value for the pressure coefficient. And this one, this value, you get it from after interpolating in tables. You see, you have plenty of tables, so plenty of interpolations to make. So you have to do it for walls, roof, and for every single possible direction, and twice per direction. So yeah, it's definitely manually, it's a chore, and you will probably mess up in the process. So you need a software to do that for you. And the worst part is that if you do it manually and the building is modified, like it gets a bit higher, or it gets a bit longer because some elements are added, well, your whole day is wasted, because you've got to do it all over again. It doesn't happen if you have a good climatic generator, because if you ever make any modification on the building or on the wind parameter itself, like you want to change like a terrain category, well, you don't need to manually recompute your forces. You can just update them, you see, and instantly you get your new set of forces. So yeah, my point is for steel design, having a solid climatic generator, it will make a huge difference. So let me just define some snow forces. So it works exactly the same way. You will set like where you are. You get some usual parameters like altitude, and you will generate the forces, and you will get the expected cases like you get the uniform snow cases, and you will get the drifted snow, like you get 50% snow and the full intensity on the other roof. So yeah, just as quick as for the wind forces. And now we can combine them. So we get the ULS and SLS combinations. And now we can actually focus on some steel design assumptions. Like, like if you want to put restraint there. So let me show you how it works. So restraints, they will help me with the lateral torsional buckling effects. So usually you would put restraints where you have bracings. You see here my bracings. These bracings, they will actually block the purlins, and the blocked purlins, they will prevent the lateral torsional buckling effects on the rafters. So it would make sense to put restraints where the bracings are. And I can do that very quickly and graphically in advanced design, just by selecting the rafters and defining restraints on selections. Like I will put them on the upper flange because the purlins are connected to the upper flange of the rafters. And I will just click where the bracings are. And once I press enter, you will actually see the restraints. So you see the green triangles here, they stand for the restraints. So they will help me reduce the lateral torsional buckling effects. So you can proceed the same way on the other rafters. And maybe you want to restrain like all rafters. And so you don't want to click all points, but you want to affect them all. So you can do that because we also have bracing. They are 4 meters long. So I can define restraints, this time by abscissa. I will put them on the top flange every 4 meters. And you see, I get my green triangle here, which stands for the restraints. And of course, if you want even more info, you can select a member, you can open a dialog where you get a preview of the element. And plenty more of options like, you get access, you get control over the critical moment, you can have it automatically computed, but if you've got a complex case, you can import the value if you have it coming from maybe a calculation table or something. So plenty of parameters for lateral torsional buckling that will help you for in the optimization process, because that will reduce the stability work ratio. And by the way, the optimization, we will define it in the steel design assumptions. You see where you can make sure the section is not overused, but make sure it's not underused either. Make sure the deflection is checked, and this is also where you will activate the imperfections, like the global sway imperfections and the local bow imperfections. And let me show you how it works. So this imperfection, we will first activate them in the strong axis of the columns. So I will select maybe these columns because they go by 3 in their strong axis. And you see the property here, global imperfections in the strong axis. I will activate it and just define, just set how many columns I have. So they go by 3. And this, so H is automatically found out by advanced design. The other one is a recommended value from zero code. And this gives you a 1/270 imperfection coefficient for the global imperfections. Then you will activate the local bow imperfection still in the strong axis, and that's it for these columns. Now we will select this other set of columns, and this time they go by 2. So here you have 2 columns, which gives you a slightly bigger coefficient, and you will activate the local bow forces in the strong axis. But you can also activate the imperfections in the weak axis. You just need to select them in a different way, because you will select this set of columns. They go by 3, 1, 2, 3. You will also activate the local bow imperfection for them in the weak axis. And this time you will select this set of columns, and you've got 7 of them. So you just put 7 there, calculate, and you give them the local bow as well, and that's all you need to do. You don't need to input the buckling curve for the local bow imperfection, because Advanced Design is able to do it on its own. And yeah, by the way, once you've introduced the imperfections, like the global ones, the local bow ones, you may want to activate also the second order analysis, because once you've got the imperfections, like global and local, and you run a second order analysis on top of that, it allows you to neglect like the buckling coefficient and the lateral buckling coefficient, like the ZY, ZZ, ZLT. You can ignore that, because imperfection and second order is enough to cover for all member possible instabilities. So at this point, I think we can run a calculation. Oh, by the way, I have some nice saved view to help me in the coming calculation report. Like I have a support view with numbering, same thing with linear numbering to show with tables. But that's definitely not the point. I will run a calculation with finite element calculation. So this will compute the elementary cases and the ULS and SLS combinations. It will give me access to displacements, forces, stresses, but be aware that for the moment it's just a first order calculation. You see? So you can still progress in the command line. If you have any error in the model, then you are warned and you're provided guidance to solve them. But here we shouldn't have any trouble. And calculation is done. So first order calculation at the moment, just so we can check if you want to make sure the deformed shape makes sense, that you didn't forget any support for like dead loads. Yeah, if you want to check some internal forces for a given load case, yeah, you can do that. Like for snow, you've got the expected bending moment diagrams. But that's not exactly what we're after. What we want now are the Eurocode 3 results. And for that, I can pick a few elements, run the Eurocode 3 analysis on them, and yeah, you can run the calculation on a selection in the latest version. And yes, please check carefully what's happening in the load cases. See, these are our initial load cases. You've got the dead loads, and you've got all the wind forces, and then you've got the snow forces. But please notice all the extra load cases that have just been created by Advanced Design in the calculation loop. You've got these are the imperfection load cases. You've got the global sway imperfection, and you've got the local bow for strong axis and weak axis. So Advanced Design, so the calculation is over, and I haven't even finished my my speech. So yes, you've got imperfection cases in weak and strong axis, and then during the calculation process, Advanced Design used these imperfection cases with the initial ULS combinations. So it's mixing like the global sway with the local bow in the same direction, because you're not supposed to mix the imperfection in the strong axis with the imperfection in the weak axis. You're not supposed to do that. So advanced design will not do that. What it will do is consider a +1 and -1 sign to consider all the possible outcomes and make sure the results are safe. And let me show you what these imperfection cases actually look like. I will pick, so I think I have some presets to help me. And I will pick first a global imperfection load case. Like, yeah, this one we can isolate. And you see, you get the expected global imperfection forces. It's a punctual load on top of a column, which is balanced by a punctual load at the bottom. And this intensity depends on the actual force. So it will be smaller for a column on the far left and a bit bigger for a column in the middle. And even though the intensity are quite small, remember that because of the second order calculation, these small forces can have a huge impact on the displacement and the internal forces. So these are the global sway imperfection in the strong axis, but you also got them on the weak axis, you see? And then come the local bow imperfections. And this time it's a set of linear forces which are balanced by some punctual load on top and bottom. And the intensity of this linear load depends on the buckling curve of the column in the strong axis and in the weak axis. But at no point did the user have to input the buckling curve. You know, it was done by advanced design during the calculation loop. So it found out the appropriate buckling curve in each plane. It created the imperfection cases. Then it mixed them with injected them in the initial ULS combinations without the user doing a thing. You know, we really wanted to minimize user input because with user input comes the risk of errors, and you really don't want that. And that way we're getting some accurate Eurocode C results. We can let advanced design run a series of optimization. At any time we can check like the Eurocode 3 results. You can pick an element, you get a detailed shape giving you like a deflections, strengths and stability verification. You even get a detailed report that will give you like all the assumptions, and for every single check you get article reference, you get the formulas and even the intermediate values, like every single coefficient is right there. So this is like Eurocode 3 by the book, but at some point you might have to go beyond the limitation of the standard. Like if you have an unusual section, like if you have a channel, and I happen to have a channel there on the platform, you see this is a channel section. So if you stick by the standard, in this case, you're pretty much on your own, because this section shape is not covered because of the torsion and warping effects. And that's why the advanced stability method we have comes in. This is where you will use it, because this method will isolate the member. The boundary conditions will be turned into a set of nodal springs, you see, and for each edge, you're given access to not 6 but 7 degrees of freedom, because the seventh one is the warping. You know, RW is for warping. So each degree of freedom can have its stiffness automatically computed by advanced design, depending on the so forces at the node and the displacement at the node, or you can like control each degree of freedom if you know that one of them is free because the member was hinged. So you have total control over each degree of freedom. Then the imperfections will come in and they will have the same shape as the critical eigenmode. So this critical eigenmode will be scaled to turn into a displacement, and that will be the imperfection. And then we will run a second order analysis on top of that to account for all possible effects. And second order doesn't mean it will be long because the calculation is quite fast. See there, it's almost instant. So it's running all the ULS and SLS combinations. You can see here how it's progressed. And even though this section is not covered by zero code 3, because it's not doubly symmetric, I will be able to get some accurate work ratio and deflection checks. Our calculation is actually longer than expected, so maybe I did something wrong. I will run again. The forces, no, forces should be okay. Do I have my, yeah, I've got everything. Yeah, it's actually a bit faster. I don't know what I did the first time, but yeah, I'm actually, calculation is done, and that way I can check the results, even though this section is very unusual. And I'm getting some deflection checks. So they include the second order displacements, and I'm also getting some cross all the strengths verification. And you see, if you're familiar with advanced design, these are extra information like normal stress, shear stress, and von Mises stress. They include all possible forces. Like von Mises stress, it will include the axial force, the bending moments in both planes if you have them. It will include also torsion and warping and not only first order forces, but also the second order forces. You also get access to the critical load factor just to make sure that this section is, in this case, way underused. So I can definitely use Let Advanced Design optimize section for me. So there is actually more I'd like to show you, but I see time is running by, so we'll have to stop there. So I hope I kept you interested in showing you the steel design capabilities of advanced design, which were a solid climatic generator, then some easy and quick ways of defining the steel design assumptions, as well as a smart management of the imperfections, but also some features that go beyond the standards, like the second order analysis with warping and imperfection that I've just showed you. And if I did keep you interested, well, make sure to visit our website. You can also contact us. And please check our incoming global digital conference that will take place beginning of June, and where you will see not only our solutions for simulation, but also our solutions for creation, simulation, fabrication, and management. So I hope to see you there. Maybe we have time for a couple questions real quick. So let me check in the panel. If you have any question, you can definitely shoot them. And I will do my best to answer. If questions are too tough, I will get back to you a bit later after concerting with my colleagues. Not sure I have any questions for the moment. Oh, I do have one. Can I get a complete material that covers the webinar? Well, you can. It depends on what you mean by material, because this webinar is recorded, so it will be available on our website. You will get a link shortly. What we can do, I think, is also provide you the model. That way you can repeat the steps. Another one, I just want to upload. Yeah, maybe it's missing some parts of the question. Oh, can you explain the global second order analysis calculation procedure, please? Well, yeah, in this case, we will use an iterative method. So the calculation will be a bit longer, and it will include a nonlinear calculation. And that way you will actually see the impact on the small imperfection forces on the final results. You will get some bigger displacement and internal forces to be used in zero code 3 design, but this is a bit long to explain, so yeah, I will provide you some information when I get back to you. The link of the webinar, it will be given to you. We've got your information, so you you will know where you can download the video. When do you think that the Eurocode 1 will receive this new shape modification? Oh, this is the new rules that I mentioned for building with horizontal or vertical discrepancies. I'm not sure when the Eurocode 1 will be updated, because we were told last year that the update was almost on its way, but it's been 1 year still, and we still didn't get the update. What I can tell you is that these rules, they've been published in 2017 for France. So in France, we apply them for almost 3 years now. So yeah, it always takes time for the official update to come out. But that's good news, because by the time they reach your country, they will be they will have been thoroughly tested and implemented in advanced design. What else do I got for questions? The panel is not easy to read. A copy of the model, probably will will put a link for the model with the video, so you can practice the steps. Okay, it turned out there are more questions than I expected. So what we will do is we will stop there the presentation for today, and I will get back to you with all the answers. So thank you all for your attention. Remember to check our global conference. Really, it's important. It's totally free. And yeah, so I hope to see you there. And in the meantime, have a nice day, be safe, and bye.